Hello, and welcome to Physics Video Optics.3, Index of Refraction, Snell's Law, and Total Internal Reflection. In this video, we will discuss the details of what happens when light travels between different media, whether it be air to water, or glass to air, or between any other substances that we can think of. In general, light slows somewhat when traveling through a medium. The index of refraction of the medium is the ratio of the speed of light in a vacuum to the speed of light in that medium. This is a unitless value because both v and c, of course, are speeds. The index of refraction is a characteristic of the material. So if light goes between two substances, its motion will change based on their respective indices. This table is a list of the indices of refraction for various materials. They say that in particular it's at the wavelength of 589 nanometers, which is what we find for most lasers that we use. But we're going to use these values for no matter what light we're talking about. Notice how similar the vacuum and air are. The index of refraction in a vacuum is 1, where the index of refraction in air is 1.0003. Because they are so close to each other, we oftentimes ignore the 0.0003 and we just say that N of air is 1. Also notice that when we talk about glass, we have to be a little bit particular and know which type of glass we're talking about, because depending on what the glass has been made of will determine what the index of refraction is. And if we look all the way down here to diamond, diamond has an incredibly high index of refraction at 2.42. And we'll come back to looking at diamond in particular a little bit later. Refraction is what we call the bending of light between media. The indices of refraction can be used as an indication to how the path of light will change when it goes from one media to the other, and that's what we need to investigate more fully in this video. So when you are looking at how light comes in, as we are here with the source in the upper left-hand corner, when light comes from a medium where it is easier to travel in, and then it goes into one that is harder to travel in, the N2 is greater, the index of refraction of the second substance is greater than the first, so theta 1 is greater than theta 2. The ray bends towards the normal. Now similarly, if we reverse the process and we have a waterproof flashlight underwater and we point it up towards the surface of the water, in this case N1 is greater than N2, and it is easier to travel in the second medium, so the light bends away from the normal. The result of this is that when you have an object that's partially submerged in a liquid like water, for example, things look a little bit strange. So for example here, the boy doesn't look like he has any legs, that his feet are really close to his bathing suit there. Because if you look at the diagram on the right, you can see that the light from the girl's feet that's being reflected off the girl's feet is bending away from the normal, and so her feet appear to be about where her knees are, which of course makes her look like she has no bottom half of her legs, and her feet are at her knees, so she looks considerably smaller. This also occurs in more common situations. Like, for example, if you have a glass with a pencil in it, the pencil appears to be broken midway because the refracted light coming from the bottom of the pencil does not line up with what we see up above. You also need to think about this if you go fishing and you aim your fishing rod where you see a fish, you will miss the fish. But if you change your aim to be lower than where you see the fish, you are more likely to catch it, because otherwise you're going to be aiming your bait above where the fish is. We put this together and we end up with what is called Snell's law. Snell's law says that the angle of refraction depends on the indices of refraction and is given by the following equation. N1 sine theta 1 is equal to N2 sine theta 2. Sometimes you'll see this written as Ni sine theta I equals Nr sine theta R for indices of the incidence and the refracted rays, but it doesn't matter which you use. In order to be able to use this law, you need to remember to measure the angle from the normal, not the surface of the material. And you also want to make sure that your calculator is in degrees and not in radians. Now, if we look at the geometry of this particular picture here, where we have a ray coming from an object in the lower left-hand side, it's approaching a piece of glass at an angle of incidence of 60 degrees. The glass is going to bend the light ray towards the normal, and then at the other side, the light is going from the glass into the air, so the light is going to bend away from the normal. So the image, where the object appears to be, when viewed from above through the glass, you're going to see that it looks like the object is over here as opposed to where it really is. So it has been moved some. Now, again, let's take a look at this picture, and you can see that you have two theta A's in the middle. This is because the sides of the glass are parallel. If the sides of the glass were not parallel, those two angles would not be the same, and theta B would not be 60 degrees like theta I is. So keep that in mind. If you're lucky enough to have surfaces that are parallel to each other, then these different angles are going to be equal. But if you aren't, you have to be careful that you don't fall into that trap that they are. So again, Snell's law, N1 sine theta 1 equals N2 sine theta 2, allows you to take a look at refraction between two media and to see what goes on. Before we get into solving some of these problems, there's another case that I want to look at, which is sort of if we go from the glass outward. So if we look at just this half of the situation. If light passes into a medium with a smaller index of refraction, like water into air, the angle of refraction gets larger. So let's just say, for the sake of example here, that this is water, and up top here is air. So N1 is greater than N2. So when the light hits at angle theta 1, most of it will reflect out at angle I. Some of it, however, will reflect back down into the ocean. If we increase that angle of incidence to make it larger, the angle of refraction will be even larger. Notice that the angle of refraction is getting the light ray to be closer and closer to the surface. Eventually, you will get to the point where your angle of incidence is going to reach what we call the critical angle. And at the critical angle, the angle of refraction is 90 degrees, like angle K here. This critical angle can be found by using Snell's law with N1 sine theta 1 equaling N2 sine theta 2. In this case, your sine theta 2 is going to be the sine of 90 degrees, which means that at your critical angle, the sine of the critical angle is going to be equal to N2 over N1, because the sine of theta 2 is the sine of 90 degrees, and that's 1. So if you are looking for what is that angle after which we won't get any refraction, that's how you find it. Now, if our angle of incidence gets even larger than the critical angle, then our angle of refraction would be so big that it doesn't refract up at all, in fact. Instead, there's no light going up, and it is total internal reflection. Total internal reflection occurs, again, when the angle of incidence is greater than the critical angle. At this point, we then go back to the laws of reflection. Many substances have molecular structures that allow for total internal reflection. Diamonds, for example, Polar bear fur, this is really cool. Polar bear fur is actually clear fiber optic like tubes that use total internal reflection to direct the sun's light and therefore heat directly to polar bear's black skin. And their skin is black so that they get as much absorption of heat from the sun as possible. Another couple examples of total internal reflection. On the left here, you have binoculars and prisms shaped in such a way that the angle of incidence here is past the critical angle, so you have total internal reflection. Similarly here, and then it's allowed to reflect out, but again, two more angles past the critical angle, so we have total internal reflection. This gives true 100% reflection, which is even better than the best mirrors can do. Now, if we look at our fiber optics here on the right, a fiber optic is created of a plastic type material, or in the case of bears, their fur, such that when the light comes in, it total internal reflection throughout, no matter whether you bend the tubes or not, so that if you put multiple small fibers together, you can get an image of your light object coming out on the other side. Pretty cool, really. All right, let's do an example. We said before that the index of refraction of diamond is 2.42. So what is the speed of light in diamond? And then let's find out what the critical angle for diamond is if you have a diamond in air. So first off, the speed of light in a diamond, remember that n is equal to c over v. So v is equal to c over n. C, remember, is the speed of light, which is 3 times 10 to the 8th meters per second. N is 2.42. So light slows down to 1.24 times 10 to the 8th meters per second. This is very slow compared to what it would be in a vacuum or even in air most of the time. Let's take a look now to figure out what the critical angle is for a diamond, and then we'll see why it's used so much for for jewelry. We said that sine theta critical angle is equal to n2 over n1. So theta c is equal to sine inverse of n2 over n1, which would be sine inverse of 1 over 2.42. So the critical angle for diamond is 24.4 degrees. This is not a large angle at all, so this is why when you have a diamond made into jewelry, the jeweler would cut the top of it into many different faces, so there's lots of different angles, so that once the light gets transmitted into the diamond, it doesn't get trapped inside, which it typically would because this angle is so small. You give it lots of faces for which the light could escape from, and you end up with quite the sparkle going on with your jewelry. Here's another one. A diver shines a flashlight upward from underneath the water at 35.2 degree angle to the vertical. At what angle does the light leave the water? Okay, so here's our water. Here's our light source. It's coming up and it is at an angle 35.2 degrees. Now it's going from water to air. So we know that it's going to bend away from the normal. And we know that we are looking for the refractive angle. So Snell's law again. N1 sine theta 1 equals N2 sine theta 2. It is actually our theta 2 that we are looking for because we want to know what it will leave the water at. So N1 is N of water, which is 1.33. N2 is air, which is 1. times the sine of 35.2 is equal to sine theta 2. Take the sine inverse of that, and we end up with theta 2. And theta 2 then turns out to be 50.1 degrees. So the angle of refraction of the flashlight is a little over 50 degrees. Last one. The critical angle for a certain liquid to air surface is 43.9 degrees. What is the index of refraction of the liquid? So we're told that this is the critical angle. So remember that we then say the sine theta c is equal to n2 over n1. We know that it's going into air, so n2 is equal to 1. N1 is what we're looking for. So N1 is equal to 1 over sine theta c, which is 1 over sine 43.9, which is 1.44. So the index of refraction of our liquid is 1.44. If you had a large list of indices of refractions, you could find out what liquid this is. Or you could have an approximation of what type of liquid this is. So the key to solving Snell's laws problems is to remember which material you are starting in. So what is N1 and theta 1, and what material are you ending in? So what is N2 and theta 2. With this, we will do some more problems, making sure that you understand this, especially when we get to going from one medium into a second medium, and then a second medium into a third medium, which we will get to in class. So bye for now.